Hi everyone, and thank you very much for coming to our talk, Win-DoS Epidemic, a crash course in abusing RPC for Win-DoS and Win-DDoS. The theme for our talk today is going to be dumb ways to die for those of you who know it, so I really hope that you'll appreciate the connection between the technical details and this funny little mobile game. My name is Yair. I'm the security research team lead at SafeBreach. I have more than 7 years of experience in security research with past research on Linux embedded and Android systems. And for more than 4 years now, my main focus lies in vulnerability research in the Windows operating system and third-party apps on it. And it's also my second DEF CON talk here today.
Hi everyone, my name is Shahak Morag, currently serving as research lead at SafeBreach, with the 7 years of experience in security research. My background includes extensive expertise in Linux kernel and embedded systems, with more than 1 year of focused research on Windows platforms.
Okay, so let's see what we're going to discuss today. We're going to start with talking about the growing DDoS threat and denial of service in general. We'll then focus on one critical denial of service vulnerability that we managed to exploit called LdapNightmare, that was the gateway for this research. We'll then present our research goals, novel techniques that we invented that focus on developers' blind spots, and see how they led us to come up with a new way to create DDoS, and also with 4 new different denial of service vulnerabilities. But just before we start our journey, let's quickly be reminded of what is DDoS. So a DDoS is created when many computers try to flood a specific target server with a huge amount of requests in order to make it too busy and finally crash, or at least to malfunction. And now we can start talking about the DDoS-related growing risks that we nowadays see. So according to G-Core Radar, there was a 56% increase in DDoS attacks in the second half of 2024 compared to the second half of 2023, and the same comparison for the first half of the year was 46%. Recently, Cloudflare even reported the largest ever recorded DDoS attack with 7.3 terabits per second. Now, creating denial of service has an obvious and large price, of course. According to Perimeter 81, which is a company by Checkpoint, each DDoS attack in 2023 cost organizations approximately $6,000 per minute, with an average total cost of $486,000. Recently, on January 1st, while most of you here were probably hungover, Shahak and I published the first POC for a very hyped denial of service vulnerability called LdapNightmare. Although this vulnerability was fixed, and this vulnerability was found by Yuki Chen. Now, although this vulnerability was fixed, Yuki did not publish the technical details about it and left us with passion to discover them. This vulnerability allowed to crash any domain controller without any need for authentication or user interaction. Our research revealed that domain controllers can be turned into LDAP clients, or more specifically, CLDAP clients. Apparently, there's a specific RPC call named DSR get DC name EX2 that you can execute on domain controllers without needing to authenticate. Then this function, in order to retrieve the information that it needs, it leads the domain controller to become a CLDAP client, and you can make it contact any CLDAP server that you want. Now, for clarification, CLDAP is just basically LDAP over UDP instead of LDAP over TCP. The rest of the exploitation chain of this vulnerability, after the domain controller became our CLDAP client, was returning a simple invalid value from the CLDAP server to the CLDAP client, which was the victim domain controller. This caused the LDAP client to crash, which led the entire machine to crash as well. That was because the CLDAP client was located in the critical LSAS process, and LSAS, if it dies, then it just reboots the entire machine. So even though domain controllers are a critical component that is heavily researched for security issues, then a blind spot in it was still discovered, and that was in the LDAP client code. Out of this fact, we extracted our research goals, which were focusing on such developers' blind spots and targeting them for more denial of service vulnerabilities. And of course, as primary targets, we chose to continue with domain controllers, which are one of the key components in an Active Directory network. So if you deny service from domain controllers, you can basically halt entire organizations. Okay, so let's see which developers' blind spots we focused on. The first one was the one that we already saw, which was client code that we can trigger remotely to communicate with us as its servers. But the second one was also interesting. We tried to understand how or where in server code developers can forget about certain security needs. Then we figured out that if the server code is transport agnostic, wrapped, and uses heavy abstractions layers, and directs the developers to only focus on the application's logic, then there's a higher chance for the developers to forget about certain security needs. Then we enumerated a few options, and looking at Microsoft's definition of the RPC protocol, we saw that Microsoft clearly states that RPC enables you to focus on the details of the application rather than the details of the network, which was perfect for us. We realized that RPC, which is one of the fundamental building blocks of Windows, is actually a transport agnostic wrapped server. Now, RPC does function in the form of a client and a server. It uses a variety of communication methods. However, developers of RPC functions that make an RPC interface do not handle the network communication. They do not handle any network aspects. They do not handle packets. They simply write functions that can be called remotely, and these functions receive parameters as if these functions were called from the same process. So our assumption was that developers are more likely to forget about mitigating network-related classic server risks when the servers that they develop are RPC servers. And once we defined our goals and the blind spots that we were looking for, we were ready to start our research process. The first blind spot that we focused on was client code, since it was the natural way to go and leverage the knowledge that we already had in the area of LdapNightmare. So as a reminder, from LdapNightmare, we understood that we can turn domain controllers into our clients effortlessly and anonymously, as they just trust any LDAP server that they are told to connect to. The client code that connected to us is the LDAP client code in Windows, and that client code is implemented inside WLDAP32.dll, and it supports both LDAP and CLDAP. Now, talking a bit more technically about the exact bug that triggered the crash in LdapNightmare, it was located in the LDAP client's logic for handling referrals. The code that parses a type of an LDAP packet named referral was flawed and crashed as a result of an invalid value in one of the packet's fields. So in LDAP, there's a concept called LDAP referrals, and this concept, which is also a type of a packet, as we just saw, enables LDAP or CLDAP servers to refer a client to a different LDAP server in case that the server does not have the needed information. Then when the client receives the referral, it normally chases these referrals to get the answers that it needs. Okay, so even though the referral process didn't really happen in LdapNightmare, it didn't really go through as part of the exploitation path. It was just a field in the LDAP referral packet that was invalid. Even though that was the case, we still learned about the referral process that we didn't know before, which gave us an idea. If we are the LDAP server and we can provide a referral, can we use that for something else other than just crashing? Maybe we can leverage domain controllers as LDAP clients instead of using that against them. It could be that we can harness their resources for a distributed denial of service. What if, instead of returning an invalid value in the LDAP referral response, we'll return a completely valid one with referrals that point towards a DDoS victim? Then, maybe we'll be able to trigger any domain controller that we want to be a bot in a DDoS botnet attack. So in a normal DDoS attack, an attacker has their own personal computer, of course, that initiates the attack and communicates with a command and control server. This command and control server communicates with many different bots that the attacker has managed already to compromise, probably. And it commands them to send a big amount of requests towards a single victim in order to flood it, and this victim is the DDoS victim. However, if we affect different domain controllers worldwide to connect to our LDAP server and use LDAP referrals to refer them to a single victim server, then this would not require us to compromise many different potential bots. And then we also don't need to have any footprint on the bots that we're using. So the first thing that we want to do if we want to supply a long list of many referrals is to remove any size limitations that we have. So far, the domain controller is connected to us via CLDAP, which is LDAP over UDP, but UDP has a packet size limit that we do not want to have. So in order to solve this, what we can do is to start with a referral to our own LDAP server. Apparently, when the CLDAP client in Windows receives a referral, it contacts the referral, it chases the referral via LDAP instead of CLDAP. So this way we can switch from UDP to TCP. And now we can try to send our referral list to our domain controllers. However, it's still not that simple. Inside WLDAP32.dll, which is the Windows LDAP client, in the function that chases referrals, that is called LDAP chase referrals, there's a call to a function that checks for duplicate referrals. This function is called check for existing referral. So in case the LDAP client encounters a referral that was already chased before, it stops chasing the referral and ends the process completely. It doesn't chase any other referrals. So does that mean that we cannot implement our idea since we cannot provide two of the same LDAP referral URLs? Well, no, that's not true. We found out that even though the LDAP client validates that there are no duplicate referrals, it does that only for the URLs themselves, and the client does not verify that the URLs are not resolved to the same IP. So to exploit this logic, all that we needed to do is to configure one subdomain wildcard record in a domain that we own to lead to the victim's IP. This completed everything that we needed for our innovative DDoS attack that we named Win-DDoS. So now let's fully understand how it works. So the attacker starts by recruiting worldwide public domain controllers by sending them the RPC call that triggers them to become the attacker's CLDAP client. The domain controllers then send the CLDAP request to the attacker's CLDAP server. The attacker's CLDAP server returns a CLDAP referral response that refers the domain controllers to the attacker LDAP server this time in order to switch from UDP to TCP. The domain controllers sends the LDAP query now to the attacker's LDAP server over TCP, and the attacker responds with an LDAP referral response containing a huge list of LDAP referral URLs, all pointing to a single port on a single IP. The domain controllers then send an LDAP query to that port on that IP, and that port can be a port of a server that is a web server, for example. Then, due to the fact that web servers do not expect LDAP packets, which are not valid HTTP packets, of course, then most of them just close the TCP connection as a result of that. Once the TCP connection was aborted, the domain controllers continue to the next referral on the list, which points them to the same server again. And this behavior repeats itself until all the URLs in the referral list are over. So, without further ado, let's see a demonstration of that. So in this video, we'll see how an attacker initiates the Win-DDoS attack in order to harness and recruit the resources of 3 different domain controllers to flood a specific victim server, victim dummy server that we set up, as you can see in the preview for the video. So let's watch it. So we have our server up and running, we initiate the attack, and we can see that the domain controllers just flood the target victim servers with many, many different requests. All LDAP. Okay, cool. So Win-DDoS can be an ideal DDoS attack. It has a very high bandwidth as it can use the power of tens of thousands of domain controllers around the world. It does not require purchasing anything, and it does not require that the attackers will breach into any devices. So no footprint is left on the bots. We believe that if Win-DDoS would not have been fixed, such an attack would have dramatically lowered the bar for attackers to conduct a DDoS attack. It can be done from anywhere in a click of a button. But there's even more. There was more to exploiting this behavior. There was a Win-DoS to find, not just Win-DDoS. After understanding that we can send tens of thousands of referrals, we thought, what will happen if we just send too many more? As we already saw earlier, there is a limit if we use CLDAP, because using CLDAP limits us to a referral list of about 64 kilobytes maximum, which is the packet size limit for UDP, so we must use TCP. But is there any other limit? How many referrals would you allow if you were Microsoft in this flow? 10? 1,000? 10,000? Well, there's no really specific number that should make sense, right? So we can see the proof for it in the fact that it's really all you can eat. As far as we tested, Microsoft did not set any limit on the referral size nor on the length of a single referral. When we tried to provide a huge list of referrals, it just took too much time on our side. Our side was the bottleneck. So if we provide huge lists, we can create huge allocations. But there's even more to that. That is because apparently the LDAP client does not release any referral URL from the list until it hits the end of the list. That means that the longer the referral list that we provide, the longer the allocation stays in the domain controller's heap memory, which can be a very, very long time. It can be a few hours even. This widens the gap between allocations and releases, and therefore returning a huge list of referrals, if done multiple times, leads to this.
Dumb ways to die. So many dumb ways to die. Dumb ways to die.
Cool. So another denial of service. The result was that we either saw Elsa's crashing, forcing a reboot, or else we saw a blue screen of death. Thank you. Okay, but there's even more. Because if we can create denial of service in domain controllers leveraging classic server risks, then we can maybe do that in other attack surfaces, such as the other blind spot that we talked about, which is RPC, the transport agnostic wrapped server that we discussed about. And with this shift, I'll hand over the mic to Shahak.
Thanks, dude. Now let's move into the second part of our talk. One of the blind spots we identified earlier has already led to a denial of service. Now we'll explore the next blind spot, transport-agnostic wrap RPC servers. First, we look for potential RPC interfaces. We search for RPC over TCP or SMB pipes. Then checks whether each interface could be accessed remotely, lacking the local-only flag. This flag restricts the RPC endpoint to local transport, blocking remote access. To have the same huge impact as referral overflow, we focus on interfaces that require minimal privileges, as usually have no security callbacks. Finding an interface is not enough. We need to add something important. Crashing a random process does little. So we focused on RPC interfaces that runs inside critical processes, like LDAP. If LDAP dies, the whole machine stops, login fails, and the OS restarts. Think for a second. If one RPC call uses a lot of memory, you'll need way fewer calls to cause major damage. So we filter for function with large, controllable parameters. Simple function without sized input wouldn't allocate enough memory to crash anything quickly. Remember O's point. Widening the gap between allocations and deallocations make resources pile up faster. We tried to call RPC methods that match this criteria, but our naive approach wasn't enough. Simply calling RPC calls that we thought would be memory consuming for the denial of service attack took ages. At first, triggering candidate calls show only a small memory increase, far too slow to trigger a crash. We needed a faster way to burn through memory. But before our first optimization, we must understand the RPC bind. The bind is the handshake. The client tells the server which interface it wants by sending the interface UUID. Then the server can accept or reject with the bind acknowledgement. According to Windows RPC documentation, the client must wait for the server bind ACK before sending the RPC call. But waiting wastes critical time. What if we use that time to send even more packets? Maybe RPC isn't really stateful, and we can send the bind and the call together without waiting for the ACK. What do you think? Will it work? We tested it by sending bind and call in a single packet, and saw that the server accepts it. It actually works. We call this the stateless RPC technique. This technique gives us three main wins. First, one pre-built packet. No need to rebuild each time. Second is bind and call in one shot. And lastly, no need to wait for any replies. You can send the next packet right away. And the impact is remarkable. Our call per second rate skyrocketed, lowering the attacker's effort for a denial of service attack. And to show this, let's dive into our first RPC function. It's in the NetLogon interface in LDAP. This call translates a list of socket addresses into site names. It's available on domain controller and is unauthenticated. The parameter entry count can be up to 32,000, which is perfect for us, a large numeric parameter. But is it really perfect? The Microsoft documentation says that the maximum value for entry count is 32,000. The limit was chosen to prevent clients from being able to force large memory allocations on servers. So, should we give up? Well, no.
Dumb ways to die. So many dumb ways to die. Dumb ways to die.
This RPC call crashes LDAP. We managed to exploit the exact entry count parameter that Microsoft claimed was protected. Each call allocates at least 8 times the entry count in bytes. At the maximum value of 32,000 entries, that's at least 256 kilobytes per call. And using our stateless RPC technique, we could send a 30,000 time packet. Repeating this call at scale exhausts memory faster than it frees, causing the DC to crash. With this, we've added another unauthenticated denial of service attack, another Win-DoS, this time via RPC instead of LDAP. So great, another new vulnerability. But we couldn't crash with other RPC calls quickly enough. Stateless RPC alone wasn't enough. We needed new crash methods. So given our DDoS discussion and the fact that we limit ourselves to only one computer, we wondered, could we create a DDoS-like attack from a single machine? What stopped one computer from opening thousands of connections to overwhelm the target like a real DDoS? And to answer that, we identified the entire bottleneck, which is everything before the RPC call. First is sending the bind packet. Second is waiting for the bind acknowledgement, as we know from the stateless RPC technique. And third is the processing time on the target. So we know the RPC call raises memory. Our plan is to split the attack into two phases. The first one opened thousands of connections by sending all the bind packets up front. And the second flooded simultaneously with RPC call to spike memory. But binding so many packets takes minutes. So how long does the server keep those idle bindings before dropping them? We wanted to know how many bindings we can send in the first phase. Remember, the more bind requests we can send, the more effective the attack will be. In our tests, Windows RPC servers kept bind-only connection open for 10 minutes, at least without timing out. That gives the attacker plenty of time to complete thousands of bind handshake before unleashing the flood of RPC calls. This means attackers can queue bind operation and then unleash a sudden flood of RPC calls, bypassing all pre-call overhead. And in simple terms, bind everything first, then flood with RPC calls later. Because this attack has an effect like a DDoS, we call it torpedoes, a single computer DDoS. On Windows endpoint, SMB RPC pipes limit to any simultaneous binding, which is bad for torpedoes. Only small amount of bind-only connection allowed. However, TCP interfaces have no such limit, making torpedoes very effective. No common DDoS mitigation, as per IP rate limits or aggressive timeout, apply here. Let's see torpedoes in action. We use the NetLogon interface in Alsace. This call is the first step of the secure channel session key negotiation. It's available on DCs, unauthenticated. Anyone with network access can trigger it. We focus on the unlimited computer name input parameter. Reversing NetLogon DLL shows that calling this RPC allocates memory via NL insert challenge, which stores the challenges. With no input validation on the challenge size, we can trigger massive allocations, tens of megabytes of memory in a single call. Our enemy is challenge cleaning. NL scavenger challenges run only every 2 minutes, cleaning challenges older than 2 minutes when a new one arrives. That window lets us build up allocation, like with referral overflow. Without torpedoes, we have a tight 2-minute window to crash via resource exhaustion. But since binding don't create challenges, NL scavenger challenges never runs. We can send much more calls in the same 2-minute window. And this is our second NetLogon RPC bug.
Time wasted time.
Now we add a new unauthenticated Windows to our arsenal. But as always, we wanted to dream even bigger. So far, we achieved denial of service for every DC. What if we could crash anything, including Windows endpoints? But as far as we could find, all RPC interfaces on endpoints required authentication. With this constraint, we returned to our first generic Windows attempt. We found an RPC in WK SSVC DLL. It reports currently enabled transport protocols for the SMB redirector on a remote computer. The preferred maximum parameter lets us allocate up to 4 gigabytes of memory in one call. We don't need to use torpedoes here. We could force the computer to allocate hundreds of gigabytes of memory with only few calls. Sounds like the dream, right? However, the computer didn't crash, and we wanted to understand why. Reversing the library shows it called local alloc with lmem0 init and our parameter. We simulated this call in Python, allocating 2 gigabytes. Then we used virtual query, a Windows API function that retrieved information about range of pages to inspect the memory region, confirming it was committed with the memcommit flag. Microsoft Docs explain memcommit assign physical pages only on first access. And that's why it didn't crash. The pages weren't accessed. Still, this confirms our second blind spot hypothesis. Developer may overtrust RPC and forget about resource abuse risks. We searched for other ways, but we were stuck. So what do we do when we don't have any lead to denial of service? We go to the pool. Oh shoot, I'm in the spool. An interesting RPC in spool SV enumerates printers, servers, domains, and providers, but it requires credentials. These limitations still allow any domain user to call it remotely on any computer. But authenticated RPC becomes stateful. Packet after the bind are signed, and we note that signing takes time. This will break the stateless RPC and torpedoes technique. We sniffed with Wireshark and saw that NTLM signing adds a major delay, and we produced the following solution. Pre-bind, capture the needed values, pre-sign the hard-coded packet, and then keep using it. And that's restore torpedoes even with authentications. We tested the impact, and we saw that in authenticated cases, torpedoes is even more relevant. We exploited the name parameter, and with pre-binding and signing, crashed the endpoint.
Dumb ways to die. So many dumb ways to die. Dumb ways to die.
Now, a single user can crash all Windows machines in a domain. And without further ado, let's see how to crash Windows 11 with Win-DoS. So first, let's see the target IP of the remote computer. And now we'll try to ping this IP in order to see that the computer is still alive. And we can see that the computer is alive. Now we'll attack the computer with torpedoes. We can see the pre-bindings happening right now. And the computer is still alive. Now we'll attack it again, and fast forward a little bit. We can see that the computer don't respond to our pings anymore. And wow, the computer has crashed. And we reach the blue screen of death. Here's our final Windows 11 Windows vulnerability, the last one in this talk. Let's recap all our denial of service attacks. We found 4 new remote trigger denial of service attacks. The first vulnerability used both for denial of service and distributed denial of service. We started with DCs and ended up with any Windows endpoint. All the DC attacks are unauthenticated, and any domain user can crash any machine in the domain. Microsoft fixed everything, and we want to thank them for cooperation. We want to emphasize that these attacks are critical. They can halt organization, damage medical equipment, or even frame governments for cyber attacks. Now we will get back to Or for our research takeaways.
Thank you, Shahak, for all of these very interesting technical details. I hope you enjoyed them. But we still have one more important thing to talk about when we conduct such a research and see its results, and that's the takeaways. So the first takeaway that we have from this research is that if code can be triggered remotely, then you should prepare for worst case scenario, concurrency, and resource usage. And you should ensure robust security measures. In MSRPC, the most likely scenario is usually one client. However, in the worst case scenario, there could be a limitless number of clients causing unexpected DOS. That's also true when talking about the LDAP client in domain controllers. Their LDAP clients can be their LDAP client can be directly triggered by a remote attacker that aims to exhaust the LDAP client's resources and exhaust the entire machine finally. Our second takeaway is that organizations must assume that all their servers and endpoints can be targeted by DDoS attacks, whether they are public-facing or not. Therefore, they should set up proper mitigations for such attacks in their infrastructures, including both defending assets, but also quickly identifying a single source creating such attacks. DDoS attacks, or DDoS-like attacks, can be single-sourced and come from within your organization, or in our words, torpedoes. And our last and third takeaway is that the fact that some forms of servers can be turned into clients can be leveraged by attackers for crafting and presenting a false image of reality for various types of purposes, or alternatively, harness resources that they do not possess for malicious purposes. For example, attackers could use our Win-DDoS vulnerability in order to trigger domain controllers from a certain country to attack a different country in order to incriminate a certain government or organization for political purposes. And with this last takeaway, we want to share with you that we believe that the Win-DoS epidemic has just begun, and we think that these techniques are just the first steps towards many more vulnerabilities in RPC. We really recommend that you stay tuned for upcoming conferences, wink wink. And generally, we encourage you to try to implement our ideas to find more of these vulnerabilities so they can be fixed before real attackers take advantage of them. So thank you everyone for joining us. This would be the QR code for the Win-DoS repository that will go live right after this talk, just 10 minutes and we'll release it. You can have the social media details of both myself and Shahak. You can contact us if you like that, and we'll be here for questions as well. So thank you everyone. Yeah. And would love to take a selfie with you if that's okay. Cool. Let's do. Thank you.